So our second speaker of this session is Nadja Egner from UC Louvain, and she'll be speaking on internal double categories and two categories in the abelian context. Over to you.
Yeah, so thank you. I'm very happy that I'm able to speak here today. So I structured my talk in 4 parts. In the first part, I want to recall or introduce you to the categorical theory of central extensions. In the second part, I want to apply this theory to an example, namely internal higher categories in the abelian context. So in the third part, I want to speak about higher central extensions, and then at the end, I want to mention 2 directions one can further investigate. Okay, so as you might know from group theory, we call a subjective group homomorphism F from a group A to a group B a trivial extension if F restricts to an isomorphism between the 2 commutative subgroups of A and B. So here the commutative subgroup is the normal subgroup generated by all the elements of the form A prime, A inverse, A prime inverse, where A and A prime are elements in A. And we call F a central extension if it's kernelized in the center of A. So here the center of A are all the elements which commute with all the elements in A. And then one can show that any trivial extension is central, and there are similar notions for the algebras or other algebraic structures. So now the question is there a categorical framework for which this is an example of? And the answer is yes. So in the paper from 1994, George Leibniz and Max Kelly consider a Bar subcategory C and a Birkhoff subcategory X of C, where here by Birkhoff I mean replete full reflective subcategory, which is closed under subobjects and quotients. So here I denoted the reflection of C into X by I and the inclusion by H. And then closed under subobjects, I mean that if we have a monomorphism in C, where the codomain is in X, then the domain must be in X as well. And closed under subobjects means that if we have regular epimorphism in C, where the domain is in X, then the codomain must be in X as well. And as an example, we can think of C as the category of groups, and as X the subcategory of all abelian groups. And then the left adjoint is given by the abelianization, which maps a group B to its quotient by its commutative subgroup. And more generally, we can take any variety of universal algebras, which yields a Bar subcategory, and then by Birkhoff's theorem, the Birkhoff subcategories of a variety are exactly the subvarieties of the variety. And now, if we fix an object B in our category C, then here the original adjunction induces an adjunction between the extensions in C over B and the extensions in X over IB. So here by extension, I mean regular epimorphism. And here can also mention that if we have an exact category C, Birkhoff subcategory X of it, then X is an exact category itself, and a morphism in X is a regular epimorphism if and only if it is a regular epimorphism in C. So here the left adjoint is just given by if we have an extension to B, then its image is just the image under I. And for the right adjoint, if we have a morphism F from X to IB, then HB of F is given by the pullback of H of F along the B component of the unit of our original adjunction. Okay, and then we call X in addition admissible if this right adjoint HB is fully faithful for all objects B. And there's a particular case where the admissibility is always fulfilled, and this is the case if C was a null subcategory. So here to remind you, a null subcategory can be defined as a finitely complete category where any internal reflexive relation is an equivalence relation. And examples of null subcategories are, for example, all the abelian categories, so abelian groups or modules or a ring, but also any semi-abelian category. So the category of groups, of the algebras, of rings, of cross modules, and there are lots more examples. And now, if we assume that we have such an admissible Birkhoff subcategory X in our category C, then the following 2 notions make sense to consider. So first, an extension F is called trivial if it lies in the essential image of our right adjoint functor HB. And one can show that this is equivalent to say that here this naturality square is a pullback. So if we think of X as a subcategory, which is easier to understand as the whole category C, then we can think of the trivial extensions as the extensions coming from this subcategory. And we call the extension F central if there exists another extension G such that the pullback of F along G is trivial. And here denotes the pullback by Q1. And so now one recovers indeed the notions of tree extension and central extension of groups if one takes as T the category of groups and as X the category of abelian groups and the abelianization factor between them. And also in this general setting, one can prove that the tree extensions are included in the central extensions. So the tree extensions are pullback stable. And then here in the definition, we can take G to be F itself. And there's also a very important result, namely that we can classify the central extensions in terms of internal actions of the Galois pre-cobalt, which is also generally. So I won't speak about the second part in the following, so I won't give you the details what this exactly means. But instead, I want to apply now this theory to an example. And for that, I want to remind you that if we have a finitely complete category C, then an internal category in C is given by such a diagram, where here on the right-hand side, we have the object of objects, C0, we have an object of errors, and then we have a domain morphism, identities morphism, and codomain morphism. And if we take the pullback of D along C, then we get the object of composable pairs of morphisms, and we have this composition morphism. And then these maps have to satisfy the usual axioms, associativity, unitality. And for an internal groupoid, we also require an inverse morphism I from C1 to itself, which then also has to satisfy the usual axioms. And if our category is abelian, then actually any reflexive graph, so a diagram where we only have the part of on the right-hand side, has a unique category structure, and it also has a unique groupoid structure, and we get this equivalence between the category of internal groupoids in A and the error category of A, where the correspondence is given as follows. So if we have a reflexive graph, then we can normalize this by taking the kernel and then composing with the codomain morphism, and then we get this error from the kernel to C0. And the other way around, if we here start on the right-hand side with an error, then we can construct a reflexive graph by taking the byproduct of A and B, and then the product projection, the coproduct inclusion, and the induced morphism by F and the identity on B to get this reflexive graph. And then we can iterate this and get an equivalence between the internal double groupoids in A, which are the internal groupoids in the category of internal groupoids in A. And so these are equivalent to the double error category, which is the error category of the error category. So here, for double groupoid, we can depict this as follows. We have 4 reflexive graphs, which all underlie an internal groupoid, and then the respective squares have to commute. And double errors are just commuted to squares in A. And then this equivalence restricts to an equivalence between the 2 groupoids in A. So here, if we consider C00 as the object of objects, and then here C10 and C01 as the object of vertical morphisms and horizontal morphisms, and C11 as the object of commutative squares, then for the 2 groupoids, we want C, so the object of vertical morphisms and the object of objects, to be isomorphic via either of these morphisms. And then the category of 2 groupoids is equivalent to the category where here in the left bottom corner we have the 0 object, and I denote this by 2 error A. And we can also think of this category as a pair of composable morphisms which composite 0. Okay, and then we also get in dimension 3 that the triple categories in A are equivalent to commutative cubes. And the 3 categories are equivalent to commutative cubes where we have 4 zeros in these corners, or we can also think of it as 3 composable morphisms where the first and the second composed gives 0, and the second and the third composed is also 0. And the way I want to think about these categories now is that via functor categories. So yeah, we've seen the double arrow categories. These are the commutative squares. So here, this is a functor category from T to A, where T consists of these four objects. We have these morphisms and then one diagonal morphism. And the two arrow A is a full subcategory of the functor category, where we want this object in the left bottom corner to be mapped to 0. So we can identify a replete full subcategory S in T, which I noted here in blue. And then the objects are the functors such that f of t equals 0 for all objects which are not in S, which is in this example exactly this object. Okay, so in the following, I will work with an abelian category and a finite category T, and then a subcategory S, and then consider the functor category A to the T, and then F, whose objects are the functors such that f of t equals 0 for all objects which are not in S. And we have in mind that examples are double categories or two categories, and then, yeah, any dimension higher. And the first result is that F is an admissible Birkhoff subcategory of A to the T. And the first thing that I want to remark is that because A is abelian, clearly the functor category is abelian as well. So in particular, it is bar exact and also Maltzer. And for the proof, first I want to show you the selection. So if we have a functor F, then we want to construct a functor in F. And so for this, I will use this notation. If we have an object T in T, then the square brackets T is the set of morphisms which land in T and where the domain doesn't lie in S. And then if we have a morphism tau from T to T prime in T, we want to construct the image of this morphism under the new functor, which I will call I of F. And for this, we consider this diagram. So here, left top corner, we take the crow product of all the domains of the morphisms T in square brackets T, and then we get this induced morphism from the crow product to Ft, which is defined by here if your T hat is the crow product inclusion of this crow product with respect to T hat. A T hat is a morphism in T prime. Then here, this is the composite is just f of T hat. And here I go from Ft to Ft hat via f of tau, and we get a commutative square on the left-hand side by taking here phi to be the morphism defined by phi of iota T hat equals iota of tau T hat. So here T hat goes from somewhere outside of S to T, and then tau goes from T to T hat. So this morphism is indeed a morphism in square brackets T hat. And then we can take the co-kernels on the top and the bottom, and we will set I f of t to be the object of the co-kernel, and we also get this morphism between the two co-kernels, which will be I f of tau. And then one can check that this yields indeed a reflector I from AT to F, and the unit eta is given, so the component of eta F, so the component, if you have, yeah, eta is natural transformation from identity functor to I, so the component eta F is a natural transformation itself from F to IF, and then here I denoted eta Ft is then the T component of this natural transformation, which is just the co-kernel. And then the fact that the unit is a regular morphism already implies that F is closed under subobjects. So for it to be a Birkhoff subcategory, we also have to show that it's closed under quotients. So we take a regular epimorphism alpha from F to G, where F is already in F, and we want to show that G is also in F. So we take an object T, which is not in S, and then want to show that G of T equals 0. But because colimits are computed pointwise, we get a regular epimorphism from Ft, which is 0 by assumption, to Gt, and then Gt must be 0. And as I mentioned, our functor category is Maltzer, so we get the admissibility for free. And as example, we can look at reflection of the double category in the two arrows category. So if we have here a commutative square in the back, then here on the top, we don't change anything. So we keep A11 and A01. Here we have 0. And then we take here the co-kernel of A to the 0. And then the composite of A1 with co-kernel A0 after A0 is indeed 0. Okay, so now that we know that we have an admissible book of subcategory of AT, we can ask what are the trivial and central extensions with respect to the subcategory. And there we have the following result. So an extension alpha is trivial with respect to F if and only if alpha T and eta Ft are jointly monic for all T in T. And if T is not an S, then this means that alpha T is an isomorphism. Why is this the case? Because if T is not an S, then we know that eta Ft is a morphism from Ft to 0. So the fact that alpha T and eta Ft are jointly monic amounts to alpha T being a monomorphism. But then alpha T is by assumption also a regular epimorphism. So alpha T is an isomorphism. And here there's not much to do, thanks to Janitz and Kelly, where we just use that for our functor category, limits and co-limits are computed pointwise. And then we also have a characterization for the central extensions. So extension alpha is central with respect to F if alpha T is an isomorphism for all objects T which are not in S. So we keep the same condition as for the true extensions for all the objects which are not in S, and we forget the condition for all the objects which lie in S. And here for the proof, we can use a result by Thomas Everett and Marina Grant from 2010, where they consider a more general framework. So here for them, C is a semi-abelian category, X is a Birkhoff subcategory, and the reflector from C to X is proto-additive, where proto-additive means that it preserves split short sequences, and then they show that an extension F is central with respect to X if and only if its kernel is an X. So here we have an abelian category. F is a Birkhoff subcategory, and in our case, I is even additive, so it preserves all short sequences. So we can apply the theorem, and here we get that the kernel of alpha is an F if and only if the kernel of alpha T is 0 for all T which are not in S, and this means that alpha T must be a monomorphism, and then as before it follows that alpha T is an isomorphism. So now we know the central extensions of the double error category with respect to true error A, for which here we get an isomorphism between the objects in the left bottom corner, and the other morphisms are arbitrary epis. And we also can construct very easy examples to see that there are central extensions which are not trivial. So for trivial, we would also have that F00 must be jointly monic with the co-kernel of A0. So I've shown you that F is a Birkhoff subcategory of AT, and I also want to mention that F is a torsion-free subcategory of A to the T, where the torsion subcategory is given by T, where here the objects are the functors, where this morphism that we considered before is an epimorphism for all T in T. And to show this, we have to prove the two axioms. So the first one is that if we have a natural transformation from a functor which is in T to a morphism to a functor which lies in F, then this natural transformation must be 0. And this is straightforward. So I won't show you the details, but I want to show you the proof of the second axiom, which is that if we have a functor F, then we can construct a short exact sequence where here Tf lies in T. And for that, we again have this morphism tau from T to T prime in T, and we consider this diagram where the back of this diagram we considered before. So here we had this commutative square with phi, and then we took the co-kernels to get IF of T and IF T prime. And now what we do is we take the kernel of eta Ft to get Tf of T, and then also we get this induced morphism. And because we are in a abelian category, the morphism from the coproduct to the kernel of the co-kernel of this morphism will be an epimorphism, and then this implies that TF is indeed in T. And then it's clear that we have the short exact sequence. Okay, and as examples, we get that 2 error is torsion-free, where the torsion objects are the commutative squares. Where we have 0 on the top, and then A an epimorphism. And also the 3 error A is torsion-free, where the torsion objects are given by such commutative groups, where we have again 0 on the top, and then A1 an epimorphism, and A2 and A3 jointly epimorphic. Okay, so yeah, in the third part, I now want to go from center extensions to higher center extension. And for that, I want to recall, so at the beginning, I started with the definition of a center extension of groups, which was a subjective group homomorphism such that the kernel of F lies in the center of A. So here, the commutator of the kernel of F with A equals 0. And we've seen that this is an instance of the categorical notion if we take here this adjunction, the abelianization from groups to abelian groups. And then one can actually show that the center extensions are a reflective subcategory of the extensions in group, where the left adjoint is given as follows. So if we have an extension from A to B, then the quotient A by the commutator of the kernel of F with A, and then this induced morphism from the quotient to B will be a central extension. And the result due to Hopf is that if F is a presentation of B, so not only extension but also A being projective, then the second integral homology group of B is isomorphic to this quotient, where we have the commutator subgroup A intersected with the kernel, and then here in the denominator we have the same. So we have the commutator of the kernel of F with A, so the same object that we needed here to turn extension into a central extension. And now I can tell you that there's also this notion of double extension of groups and central double extension of groups, where double extension of groups is such a commutative square of subjective group homomorphisms, such that if we take the pullback of these two morphisms, then the induced morphism from A to the pullback is subjective as well. And then central double extension satisfies these two properties as well. And one can show again that the central double extensions are reflective in the double extensions. Where here, if we have such double extension, then we take the quotient by C, where here C is the product of these two subgroups, and then we get induced morphisms to A1 and A2, and then this square is central. And then I saw to Carl and Alice, but also to other people, is that the third homology group of B, if this was a double presentation, so A1 and A2 being projective, then this is isomorphic to here the commutator subgroup of A intersected with both the kernels of F1 and F2 quotient by C. So here again we have the same object in that we quotient by. And so another question is this also an instance of a more general categorical theory? And is there also this link, can we establish also this link to homology? And the answer is again, yes. So here I'm using, telling you results by Arr² from 2014. So we can start with exact mass of category and a Birkhoff subcategory X of C as before. And then I will call E the class of regular epimorphisms in C. And then we've seen these two definitions of Jury extension and central extension. So here, Jury extension was a morphism F in E such that this naturality square is a pullback. And for central extension, we had another morphism G in E such that the pullback of F along G is a Jury extension. And also in this general setting, we get that the central extensions are a reflective subcategory of the extensions. And here I want to note that we can see the extensions as a full subcategory of the Arr category corresponding to E. So now we have this adjunction, and the question is, can we do the same what we did before? And yes, we can. So if we now define E1 to be the class of double extensions, where here a double extension is a morphism from extension F2 to an extension from A1 to B, such that all these morphisms are extensions. So again, we take the pullback, and then the induced morphism from A to the pullback must be an extension as well. And then we can define trivial double extension to be a morphism in E1 such that this naturality square is pullback, where here eta1 now denotes the unit of our new adjunction, and the central double extension is a morphism E1 such that exists G in E1 such that here Q1 is a true extension. And then one can again show that the central extensions with respect to this adjunction are reflective in the double extensions. Here again, this is the full subcategory of the double arrow category corresponding to E1. And then one can define triple extensions, and one gets an infinite chain of such adjunctions, which all have this admissibility condition. Okay, and the last thing that I want to tell you is that we also have a characterization of higher central extensions for our example. So if we have such a double extension in AT, then this is central with respect to F, if and only if alpha1t and alpha2t are jointly monic for all objects which are not in S. And here we can again use the result by Everett and Kran in the same paper, where they show that F1 and F2, so this corresponds to alpha1 and alpha2 here, are central with respect to X, if and only if the intersection of their kernels lie in X. Okay, so now what generalizations are possible? So here, if we want to weaken our assumptions on A, we can ask A to be only semi-abelian, and we still have that F is a Birkhoff subcategory of AT, but its reflector is not necessarily proto-additive, as it was in this case, and it's also not necessarily torsion-free. So the question is, what can we say about the higher central extensions in this case? And for the central extensions, we get the same, and I believe that it's also true for the higher, but I still have to check that. And the other question is that, so if A is semi-abelian, then we no longer have the equivalence between the internal groupoids and the arrow category, but we have to replace the arrow category by internal cross modules in A, where we have an arrow and then also an action of the codomain on the domain, which satisfies two equations or two conditions. And then, yeah, the question would be, how can we incorporate actions in this approach? Okay, so here are my references, paper by Jens and Kelly, and then paper Everett and Kran from 2010. They also have this paper which studies related things from 2015, and the paper by Everett. Yeah. That's all I want to tell you. Thank you for your attention.